Energy conservation is one of the 5 fundamental conservation laws in the universe, all based upon observed symmetries. Now, most students really care about is solving energy conservation problems. And it's a great skill to have because energy conservation, being as it's one of those 5 fundamental conservation laws, holds true from the particle physics level all the way up to astrophysics. Now, energy is always conserved within a system. The big system being our universe, and the total amount of energy in the universe always stays the same. But we can also consider a roller coaster system. What I mean by roller coaster system is I just mean the stuff here, basically the roller coaster cart. And I'm not including the atmosphere, for example. And this is a great approximation because very little energy leaves the roller coaster system. There is a tiny bit of friction and a tiny bit of sound, you do hear it, and that takes energy, and that leaves the roller coaster system, goes into the atmosphere. But it's a very tiny effect. So we're going to assume that all of the energy stays in our roller coaster system. And that's what almost all of your problems will assume as well. So now let's attack this problem. Let's say, for example, we want to find the speed at point B. Well, energy is conserved. So we know that the initial energy equals the final energy. Well, the initial energy in this case is the energy at point A, and the final energy in this case is the energy at point B. Well, at point A, what types of energy do we have? Well, we definitely have potential energy. We've put the bottom of the roller coaster as our h equals 0 point, and here we have h equals 50 meters. So the roller coaster starts off 50 meters above the low point. And so that gives us potential energy of gravity. And then there is no kinetic energy because it's not moving. So let's go to the other side. Well, at point B, you're still 25 meters off the ground. So you have potential energy plus it's going to be moving. So we have kinetic energy as well. Now we can plug in the numbers. The potential energy of gravity is mgh, where it's h at point A. Potential energy here is mgh at point B, plus the kinetic energy, 1/2 mv squared. Now, let's simplify our lives and divide both sides by m. Now here the m's cancel, and here as well you've got this term plus that term. The m's cancel in both. Or if you want to be more mathematical, you could first factor the m out and then see the m's canceling. Now, this is important. Notice that the equation we have does not include the mass of the roller coaster. So we have g times the height at point A equals g times the height at point B plus 1/2 v squared. The speed of the roller coaster at point B is not determined by the mass. It's independent of mass. This is a very good thing, because that means the roller coaster will go the same speed whether large people or small people get on. So let's now put in the numbers and work this out. So for g, well, that's the acceleration of gravity, 10 meters per second squared, multiplied by the height at point A, which is 50 meters. And then on the other side, similar, the acceleration of gravity, the height of 25 meters, and plus 1/2 v squared. So now it's just a matter of multiplying and solving, and well, here we'll get 500 meters squared second squared. That equals to 250 meters squared second squared, plus 1/2 v squared. And now just doing some simple algebra, we subtract the 250 from both sides. Guess I should put in the units. And we end up with 250 meters squared second squared is equal to 1/2 v squared. Again, a little algebra, multiply both sides by 2. Cancel, cancel. 2 times 250 is 500. I'll go up top here. So we get 500 meters squared, seconds squared, equal to v squared. And now we take the square root of both sides. Remember, when you square or take square root, you're also doing it to the units. So meters squared over seconds squared becomes meters per second. Square root of 500, 22, about 22 meters per second. And then that's equal to v, the speed at point B. Very good. Now, let's find the speed at point D. So what's the speed at the very bottom? Well, energy is conserved. So the energy at point A equals the energy at point B, also will equal the energy at point C, and equals the energy at point D. So I could either start with the energy at point B and set that equal to the energy at D, or I could start with the energy at A. I'll choose the energy at A, since it just has one term. So the energy at A equals the energy at D. And we have just potential energy, so just mg, h. And at point D, the height is 0, so there is no potential energy. There's only kinetic energy. 1/2 mv squared. And then that's the speed at point D. So going a little faster this time, I'll cancel the m's from both sides, so divide both sides by m. And I'm just left with the 10 meters per second squared times the height at point A. And that's equal to 1/2 times the speed at point D squared. Well, this is 500. And again, multiplying both sides by 2. Cancel, cancel. 2 times 500 is 1,000. 1,000. And finally, taking the square root of both sides. Well, square root of 1,000 is about 33. So the speed at point D is equal to 33 meters per second. Very nice. One small note to make is that even though this is halfway down, the speed is much more than half of the final speed at the bottom. And if you review your kinematic stuff, you'll understand why. And I'll leave it there. Let's talk about this guy. This is a pendulum. And if we hold it up here, we've now increased its potential energy. And if I let it go, it goes from potential energy to kinetic back up to potential. So what I'm saying here is that if we take the trace of its motion, I'm not too good at this, let's try this again. So something like that, we can see that at the very bottom, it's all kinetic energy. At the very top, it's potential. And then here, it's also all potential at its high point on this side. And then in between, it's potential plus kinetic. And a pendulum conserves energy very well. There's very little losses from the pendulum system, which is the mass and the string. Only a little bit of friction right here, where you might take some energy out of the pendulum system and into the environment. And that's why it does eventually slow down and come to a stop. To find the speed at the bottom, you would employ the same method we just did with the roller coaster, but using this as the height. This is the low point, so this would be the height, the increase in potential energy. So, there you go. Hope this gets you a good start on the energy conservation problems.